Have you ever noticed how some things just seem to, well, defy expectations? That ancient appliance still chugging along, maybe, or a critical piece of infrastructure that stood for decades longer than anyone predicted. Sometimes the secret isn't just in the design, but maybe in the hidden forces within the material itself, like a kind of built-in history.
Exactly. We often focus on the external forces, the loads, the environment, but these hidden internal stresses and strains, they can really dictate a material's true resilience, sometimes in ways we're only just starting to fully grasp.
Yeah, it's like we assume materials start as a blank slate, but they don't, do they? They carry this history from how they were made.
Precisely. Manufacturing itself imparts a character.
And today, we're doing a deep dive into exactly that, the fascinating world of material science. Specifically, we're looking at a paper called Analyzing the Effect of Residual Stresses on the Fatigue Life of Cold-Drawn Steel Wire Specimens. This is based on research by Danielle Lopez-Zeden, Paulo Pedro Canedi, and Luis Felipe Guimarães de Souza, just published today, actually July 9th, 2025, in Fracture and Structural Integrity.
Wow, really fresh research then. Hot off the press.
Absolutely. And what's really interesting, I think, is how they bring together two really crucial concepts in mechanical engineering.
Right. One is fatigue. Most people have heard of that, things breaking after being loaded again and again. It's a huge cause of failure.
Definitely. And the other.
The other is its sort of counterpart, residual stress, often less known, but just as powerful. It's the stress locked inside a material even with no external load.
Okay, so fatigue and residual stress. And we're going to explore how these two combine.
Yes, how they interact to determine how long a material actually lasts.
So our mission today is to unpack this pretty technical paper, pull out the key insights, make it accessible, and highlight some surprising stuff, especially for industries like, say, offshore engineering, where strong materials are just critical. We think you'll walk away with a much deeper sense of why some materials seem to, well, defy the odds. Let's get into it.
That's good.
So, to start us off, it's worth just stressing that both fatigue and residual stress cause countless mechanical failures all over the place.
Absolutely. In bridges, aircraft, engines, you name it.
And this specific research zooms in on mechanical engineering applications,
Right.
particularly using cold-drawn steel wires. You find these everywhere, right?
Oh, yeah. Bridge cables, springs, tire reinforcements, ropes, even deep-sea umbilicals. Very common material.
And what sets the study apart, you were saying, is the approach.
Right. A lot of the work out there on residual stress is experimental, measure things, test things. But this team developed an analytical model. They wanted to combine fatigue and residual stress mathematically.
So calculating and predicting effects, step by step, not just observing.
Exactly. A more predictive theoretical approach grounded in mechanics.
Okay, so talk us through their model, phase one.
Right. Phase one of their model mimics an experimental step. They start with a steel wire specimen, and they deliberately impose what's called a monotonic displacement.
Okay, what does that look like?
Imagine a round tool pressing down sideways, transversely, onto the wire. And the wire is supported underneath, kind of like a tiny bridge. It's a standard setup called three-point bending.
Okay, so you're basically bending it permanently a little bit.
That's the key. You bend it enough to partially yield the cross-section. Some parts deform plastically, meaning they won't fully spring back. So when you remove that load, the material does spring back elastically, but not completely. And crucially, this leaves behind a pattern of locked-in stress, a residual stress distribution across the wire section.
That's the internal stress we talked about, left over from that bending.
Precisely. It's now part of the wire's internal state.
And here's something I found really interesting. They noted that for parts that get yielded quite a bit in this process, the residual stresses right at the border between the elastic part and the plastic part, that stress can actually be higher than the stress right on the outer surface.
Yes. Isn't that counterintuitive? You'd think the surface takes the biggest hit.
Right.
But mechanically, that transition zone, the elastic plastic border, it can lock in more intense stress. It tells you something about how stresses redistribute internally when you yield a material.
Fascinating. So that's phase one, deliberately introducing a specific residual stress pattern. What's phase two?
Okay, phase two is the fatigue test. They take that same specimen, the one with the new residual stress, and importantly, they flip it upside down compared to phase one.
Oh, why flip it?
Well, think about bending. Phase one likely created tensile residual stress on one side and compressive on the other. Flipping it changes how those stresses interact with the next load. So they flip it, and then they apply a variable transverse load. Basically, they push on it repeatedly, up and down, using a testing machine.
Until it breaks.
Until it fails completely through fatigue. They measure how many cycles it takes.
And just for context, this experimental side was done in Brazil, right?
Mm-hmm.
At the Lemat laboratory at CFEJ in Rio.
That's right. Using a proper servo-hydraulic machine, an Instron 8801, standard but high-quality gear.
And the wires themselves. Just standard issue.
Yep, 25-centimeter long pieces, about 14 millimeters by 6 millimeter cross-section, taken directly from standard manufacturer spools of cold-drawn steel, off the shelf, essentially.
Okay. Any challenges in the testing?
They did mention one thing. Adjusting the machine's control system, the PID feedback, was tricky for these wires because they're quite flexible.
Ah, okay.
So that meant they couldn't run the fatigue tests super fast. They were limited to about 10 cycles per second, 10 hertz.
Still pretty fast, but maybe slower than they'd ideally want for quick experiments.
Potentially, yeah.
And they even did this extra check with yellow markers, groups A and B.
Oh, yeah, that was interesting. They marked the wires to see if it mattered which way up the wire came off the original manufacturing spool. You know, did it have a top or bottom from coiling?
They did it.
Yep. The results for Group A and B were, as they put it, quite similar. So that initial orientation didn't seem to play a role. Good to rule that out.
Always good to check those variables.
Yeah.
Okay, so they've induced stress in phase 1. Now they're fatigue testing in phase 2. What did they expect to happen?
Well, here's the kicker. They intended for this combination of induced stress and fatigue loading to be pretty severe. They were actually aiming for short lives. They wanted the specimens to fail relatively quickly, you know, to finish the experiments efficiently.
Makes sense from a practical point of view.
But the specimens delivered a surprisingly long life.
How long?
The actual number of cycles they lasted, they call it NXP, experimental cycles. It massively exceeded the number of cycles their model predicted, NTO, theoretical cycles.
Massively, like double, triple.
No, like nearly an order of magnitude longer.
Wow, so 10 times longer, roughly?
Something in that ballpark, yeah.
Yeah.
A huge difference, not just a small error margin.
Okay, that's genuinely surprising. So their model, designed to predict this, was way off. Why?
That was the big question. And it forced them to revisit their initial assumptions. The key assumption they'd made was that the wires, as they got them from the manufacturer, did not have appreciable residual stress. They assumed they were starting close to zero stress internally.
And that assumption was wrong.
Completely wrong, it turns out.
The aha
moment. Exactly. They realized that the residual stresses they put in during phase 1, well, those stresses weren't enough to wipe out beneficial compressive residual stresses that were already there.
Already there from?
Probably from the original manufacturing process itself, the cold rolling or cold drawing that shapes the wire.
So the factory process itself had already built in some protective stress, a hidden gift.
That's what it looked like. This pre-existing hidden compressive stress from manufacturing was the secret sauce giving the wires their unexpected extra life.
Incredible. So how did they explain how this hidden stress worked? 2 theories, right?
Yeah, they explored 2 main possibilities. First was the resistance increase idea. Maybe the material itself just got tougher somehow. Perhaps that 6% strain they induced in phase 1 actually increased the material's inherent fatigue resistance.
So the material fundamentally changed and became stronger?
That was one thought. But the second theory, which they felt was more reasonable from a mechanical engineering standpoint, was the stress reduction approach. This suggested that the pre-existing compressive residual stress, mainly near the surface from the cold rolling, this compressive stress acted to counteract the tensile stresses applied during the fatigue test.
Okay, let me make sure I get that. So it's not that the material got intrinsically tougher, but the effective stress it actually experienced during the fatigue test was lower.
Precisely. Imagine the applied tensile stress trying to pull the material apart, but there's this built-in compressive stress already squeezing it together. The net effect is a lower overall tensile stress doing the damage.
Like an internal shock absorber, sort of canceling out some of the bad stress.
That's a good way to think about it. It reduces the peak tensile stress that drives fatigue cracks.
And this stress reduction idea, that's the one they lean towards.
Yes, they found it more mechanically plausible, and it has really big implications.
How so?
It means that manufacturing processes, things like cold rolling, cold drawing, shot peening, lamination, they don't just shape the part. They can inadvertently embed these beneficial residual stresses that dramatically extend fatigue life. It's a hidden benefit of the process.
Even after the researchers deliberately added new, quite severe tensile residual stresses in their experiment.
Exactly. Even after that phase 1 bending, the original beneficial compressive stresses from the factory were still there, still doing their job, prolonging the wire's life.
That is a really powerful takeaway. It improves our fundamental understanding, doesn't it, about how residual stress affects fatigue in these kinds of wires.
Absolutely. And think about the practical side. Industries like offshore, oil rigs, deep-sea cables, pipelines, they rely hugely on the long-term integrity of steel wires and components.
Yeah, failure is not an option
Yeah,
there.
really. So understanding these built-in stresses, knowing they might be there, maybe even how to harness them, that's critical for safety, for efficiency, for actually predicting how long a component will last in the real world.
It could change how you design things, how you inspect things, how you predict maintenance cycles.
All of the above, it brings that hidden manufacturing history right into the lifespan calculation.
Okay, so let's just recap then. We've journeyed through this interplay of fatigue and residual stress in these cold-drawn steel wires. We went from the analytical models and the lab experiments to this really surprising discovery.
Mm-hmm.
And the key takeaway seems to be how this hidden beneficial compressive residual stress put there during the original cold rolling or drawing played this massive, undeniable role in making these wires last way, way longer under fatigue than expected.
Yeah, the theory predicted failure much earlier, but that hidden stress from manufacturing acted like a shield, really, a silent gift from the factory floor extending its life.
It really shows how a seemingly mundane step in making something can embed this unexpected, quite profound durability.
Absolutely.
Which leaves us with a question for you, the listener, to maybe ponder. What other subtle built-in benefits, or maybe even risks, might be lurking inside the everyday materials we rely on, just waiting for us to uncover their full, complex story hidden beneath the surface?